experiment 3, and we are working on single displacement reaction and double displacement reaction. The single displacement reaction can be, that you will observe today, can be of 3 types. Metal displacement, so a metal that is more active than another metal can displace the second metal. We can have a hydrogen displacement from acid or hydrogen displacement from water. We learned that during class. Hydrogen displacement from water happens with the elements from the first group, here, which are the most active elements in the periodic table, and second group, particular calcium strontium barium. These are the most active elements. And how does it happen? Here is an example: sodium plus water gives displace the hydrogen. So the sodium takes the place of the hydrogen. The hydrogen is displaced as a gas, so we will be able to observe bubbling, and we form sodium hydroxide. For metals that are in the transition metal group, we need to have more active, something stronger than water to displace the hydrogen. And so, for example, for zinc, we learned in class, we need one of the 7 strong acid, nitric acid, to give zinc nitrate and hydrogen displacement. Again, to get the bubbles. Metal displacement, we already said, happens with the first group of metals. How do we, if we cannot perform all the reactions today, right? So how do we predict the rest of the reaction that you work on for the at-home assignment? We use the activity series that you have in appendix A, B, or C. Which one? Do you remember? Which one is the appendix that you needed to use? Is appendix, let's take a look. I had it here. So is appendix B, this one in your textbook, and appendix C, okay? Okay, the other set of reactions that we're performing are double displacement reactions, okay? And we can have 4 types of reaction that we're going to study on today. Precipitation reaction. So we have silver nitrate with hydrochloric acid that gives a precipitate. Plus water. For this reaction, we need to know how to write the molecular reaction, the ionic reaction, and the net ionic reaction. How do we predict what is the precipitate when we're performing a reaction? What do we use? The solubility rules. So the solubility rules are appendix A, okay, in your handouts. The other type of reaction that we can form is that we can have is formation of a weak acid or a weak base. This happens when a salt of a weak acid or a salt of a weak base react with a stronger acid, in this case, to give sodium fluoride, reacts with hydrochloric acid to give sodium chloride and hydrogen fluoride. Hydrogen fluoride is a gas, so you see that. Now you don't have this reaction in a reaction to perform. I just wanted to give you an example because you learn on the first day of class what the hydrochloric acid does, right? What does it do? You remember?
Breaks down.
It dissolves your bonds. Okay? So we don't want to use that. Neutralization reaction. You have to count that part. Okay, neutralization reaction. A strong acid reacts with a strong base to give a salt plus water. Remember that we have 7 strong acids. You should have them listed in your card for the upcoming exam. And so, for a strong acid reacting with a strong base, the net ionic reaction is always this: H plus OH minus, that gives H2O as a liquid. Remember that when we write that net ionic reaction, whatever is a pure solid, a pure liquid, or a pure gas is what dictates what is written in the net ionic reaction. Those compounds do not dissociate, and so they stay in the reaction. The last type of reaction is gas formation. So here we have sodium bicarbonate that reacts with hydrochloric acid to give sodium chloride. Carbon dioxide, that is a gas, and so you will observe bubbles, plus water. Now we can have a different type of gas formation. We said that if we start, for example, from sodium, hydrogen, sulfate or sulfite? Sulfite, in the presence of the same thing, hydrochloric acid, will give nitrogen chloride, aqueous, plus sulfur dioxide, gas, plus water. We can perform the same reaction with a base, a weak base, for example ammonia, and that's why I provided you with Appendix L, because you can see all the possible reaction the ammonia can give. We can have precipitation reaction, we can have gas formation, and the neutralization. So they're all listed here. Okay? Okay. So please use this to complete your work on experiment 3 and experiment 4 that we're going to do later. In your notebook, you will need to write, for whatever is provided in space, the following observation. When you're performing the reaction, do we see a metal decomposing? That means that we have a metal displacement. Okay? Do we see a metal changing color? We need to write it down. Do we observe gas formation? And let's make sure that we don't confuse gas formation with oxygen that is dissolved in water. Because sometimes students think that they have this strip of metal, they see some bubbles on the metal, but that's air. Those are air bubbles, okay? So gas formation, we should see an evolution of gas, and for ammonia, we're going to use the litmus paper, which is an indicator of the formation of ammonia. We're going to observe if our vial gets hot, so if we have heat development in our reaction, if we have a change of color of the solution, if we form cloudiness. Cloudiness is also a form of precipitation. some reaction, depending on the activity series, might take place more slowly than others. So hold the test tube that you have been, in which you have been mixing your solution for the one in which you don't see an immediate reaction for 10 minutes to see if slowly something is happening. Okay? And then record your observation. So for part 1, single displacement reaction, we're going to add nickel trichloride in tubes 1A and 1B. Then we're going to add silver chloride to 2A and 2B. And finally we're going to add the sulfuric acid, 3 molar sulfuric acid to 3A and 3B. To each tube that has the A letter, we're going to add the copper. So 1A, 2A, and 3A. And for each tube that has the letter B, we are going to add the zinc. 1B, 2B, and 3B. And then we'll observe if we see any change. We're going to let the solution sit for about 10 minutes. And we already can observe there is a change in color in 1A, in which we had the nickel chloride. We're going to see a major change in 2B. Look, the metal is already coming apart, so it's reacting with the silver nitrate. And here we have the sulfuric acid with the two metal. So the reaction that we saw happen immediately is the reaction of 2B. To help ourselves understand what is happening in solution, first we let it sit, but we also use the activity series that is in Appendix B to see what we should expect if we can have an hydrogen displacement or if we can have a metal displacement in the two reactions. Let's wait 10 minutes and let's see if we see any change.
After 10 minutes have passed, let's observe what happened in these single replacement reactions. 1A. 1B, and 2A, and 2B, and 3A, and then 3B.
Different type of single displacement reaction based on the activity series, right? We can have a metal displacement. We can have hydrogen displacement from water. And then we can have hydrogen displacement as a gas displacement from acid. That's what we said earlier at the beginning of the lab. Now that I have all my setup to show you the very first reaction that you have in your list for hydrogen displacement from water, the reaction is we are going to describe. We have sodium solid plus water as a liquid that gives sodium hydroxide aqueous plus hydrogen as a gas. Is this reaction balanced first of all? What do we need to do to balance it? 2 molecules of water, that's correct. And that's all we need to do. If I have 2 oxygen here, I'm going to have 2 oxygen here. So I need the 2 sodium here, right? It's now balanced. 4 hydrogen, 1, 2, 3, 4 hydrogen, right? Okay. So let's perform this first reaction that you're not going to perform for safety reason, and that I am performing. Hopefully the goggles will protect me enough. So I don't know where I put them. Okay, so we have a glass watch. Let me fill this with water. 1 second. Okay, so here is my sodium. It's a metal. It is in the group 1, and notice is stored in mineral oil. The reason why it's stored in mineral oil is the sodium is very reactive. So when exposed to the oxygen of the air, it reacts to form sodium oxide. Sodium oxide is, you see that the color is kind of dull, is not shiny. Metals are normally shiny, right? So let's take another piece of metal, a big chunk here, and let me cut a piece. So it's a very soft metal. We can cut it with a knife, kitchen knife. If you can see, the metal inside that hasn't been oxidized yet is very shiny. As soon as it gets exposed to the air, it starts to become a dull color because the oxidation reaction of sodium is already happening in the presence of oxygen. So let's see what happens if sodium, a piece of metal, and I'm going to cut even smaller because it can be dangerous, is placed in a beaker full of water. Ready? So we see the hydrogen, and it even catch fire because we not only form hydrogen, but we also develop heat. And I should tell you this story. You guys want to see it again?
Yeah.
A big one?
Put the whole thing in there.
No, I'm not going to put the whole thing in there. So let's do one more time. Ready? So the smoke is also hydrogen that is developing, and the reaction is very exothermic. We'll learn later on in thermochemistry that an exothermic reaction is a reaction that yields heat and flames. So this is it. One thing that we can tell, sodium hydroxide is a base. So as we will learn when we will perform titration, we can indicate if a solution is basic by using phenolphthalein. Phenolphthalein is an indicator, and we'll learn about indicators later on, that tell us if a solution is acidic or basic. If the solution is acidic, the color of the solution stays unchanged. So here it's clear, stays clear. If the solution is basic, it becomes a different color. This is clear. You see that it's clear? The phenolphthalein. Look at this. So when the solution is basic, the solution becomes pink. Okay? So this is the whole demo. Okay, we are done with this. And you understand why
this is for set 4, 5, and 6. So for 4, we're going to be using 0.1 molars of nickel 2 chloride. We're going to add approximately, according to mixing directions, 2 milliliters. Now we're going to add 0.2 molars of the sodium carbonate. Mix it. For set 5, we're also going to be adding 0.1 molars of nickel chloride. We're going to be adding 0.1 molars of silver nitrate. Okay. For set 6, we're going to be using 0.2 molars of sodium carbonate. After, we will add 0.5 molars of hydrochloric acid. This is for set 7. We're going to be adding ammonium nitrate. Then we'll add sodium hydroxide. Now we're going to add the test tube in the warm hot water, and we'll place a litmus paper in the test tube for any vapors. This is for set 8. It'll be with copper 2 sulfate. Now we add sodium phosphate. For set 9, we're going to be adding zinc sulfate. And we'll be adding ammonium sulfide. And there's a strong, pungent smell coming from this set. Okay. Now for set 10, we're going to be using nickel 2 chloride. add ammonium sulfide. There's a pungent smell coming from this set. This is for set 11. We have sulfuric acid. We have sodium hydroxide.